The following set of video notes will cover sections 4.3 to 4.6 in the text. This will be our first part of our conformational analysis unit. So earlier sections of chapter 4 included nomenclature. Here we're going to change gears and look at analyzing different structures in terms of their relative stability and their energies. So before we can begin analyzing structures, let's take a look at the different structures that we might encounter, which might be isomers. Isomers are different structures with the same formula. And we should know at this point, which we've covered this, that constitutional isomers differ in the connectivity. So they have the same formula, but a different connectivity of the atoms. And as we increase the complexity of our molecules, namely the number of carbons, the number of constitutional isomers also increases. So as our molecules get larger, we increase the number of constitutional isomers. So the utility of this in this part of the text is being able to recognize a compound as either being an isomer or the same compound. Now we're going to be dealing with bond rotations, and we have to be mindful that a simple bond rotation could often lead you to believe that you're dealing with a different structure. So let's look at all of the possible constitutional isomers of C6H14. That's a form of hexane. So we draw our straight chain, that's 1. We have a single branch, which would be 2. We can put the branch on a different carbon, 3. We can have 2 branches, giving us isomer 4. And you can put the second branch on a different position, that's 5. And you might come up with an alternate isomer 6 here. Now, we need to test to see if our isomers are actually different molecules or if they're the same molecule. So what you can do is test to see if they're identical using one of the 2 methods. You can flip one of the molecules in 3D space and rotate around its single bonds until it's superimposable on the other molecule. For instance, if we rotate this one here, if we rotate this single bond, and so let's call this carbon 1, 2, 3, 4, and 5. So let's start with carbon 1, 2, 3, and there's 4, and I'm rotating that single bond. There's that branch. We see that these are actually the same molecules. So by rotating around a single bond, we can determine if they're different or the same. Another method to determine if molecules are identical or if they're actually constitutional isomers is to simply name them. So the 2 examples from before, if we name the first one, we get 3-methylpentane. And if we name the second one, we also get 3-methylpentane. So by naming them, we see that they're identical compounds. And 180-degree rotation around that C3-4 bond axis makes it a little more obvious. All right, moving on to section 4.4, we're going to look at the relative stability of isomers. Just of saturated hydrocarbons here. We're not going to worry about anything else yet. The relative stability of isomers can be determined by measuring the heat of enthalpy. So you should know that any hydrocarbon, C something, H something, can be combusted to produce CO2 and H2O. This is the reaction that's typical for all complete combustions. So we can think of the enthalpy, which we're going to measure, as the potential energy that's stored in the bonds. And the change in enthalpy will be the heat released or absorbed by the system during that chemical reaction. So combustion reactions typically release heat. Therefore, our delta H value will be negative. A negative delta H means that the reaction is exothermic, which means that the system will release heat to the surroundings. And let's compare several different isomers of C8H18 with different branching patterns. So we can see that the straight chain alkane, when combusted, releases negative 5,470 kilojoules per mole. When we add two substituents, okay, we have our two branches there, it releases less energy. And finally, when we have it fully branched, okay, it releases even less energy. So look at your y-axis here. This is your delta H, or your potential energy, delta H in kilojoules per mole. And we see that the branched isomer has a lower potential energy. It releases less energy. So this is what we consider a more stable isomer compared to the straight chain, which is higher in energy. It has a higher potential energy. So what we can conclude from this, by comparing the enthalpy of combustion for isomeric alkanes, namely C8H18, that's octane, different forms of octane, we see that the more branched our isomer is, the more stable or lower in energy it will be. So stable isomers, like the branched isomer here on the right, is lower in energy, meaning its reactivity will be lower and less energy is released upon reacting. So branched chain alkanes are typically lower in energy and more stable than straight chain alkanes. So in our comparison of isomers, the greater the degree of branching, the more stable or lower the potential energy that particular structure will be. All right, so we know how to compare the relative stability of isomeric alkanes by looking at combustion analysis data. But now let's look at a qualitative perspective initially using Newman projections. So single bonds can rotate freely, and as a single bond rotates, we call these rotational states conformations. So there are multiple conformations of a particular molecule, like when we were rotating around the C3,4 bond axis of the original isomer, we saw that it looked different, that those rotational states are simply conformations. So there's oftentimes where these three-dimensional conformations are difficult to represent on two-dimensional paper. So we need a way of representing these rotational states in 3 dimensions so that we can first qualitatively analyze these structures for their stability, relative stability, and 2, then we're going to quantitatively assess them by looking at certain structural features that cost energy. But that's down the road. So the ways to represent a molecule in 3D is using wedges and dashes. Right? This is all for ethane now, wedges and dashes, which we've seen before. The sawhorse and the Newman projection, which will be the focus of our discussion in the next few slides. So different conformation, different rotational states, as I rotate around this bond, as I rotate around the bond, as we rotate around, will be higher or lower in energy. So that's the point. We're doing conformational analysis, and we want to analyze different conformations being higher or lower in energy. All right, so let's really dive into Newman projections, which is going to be the focus of the next several slides. Newman projections are perfect for comparing the relative stability of these different rotational states or conformations. A Newman projection is simply a perspective looking down a particular carbon-carbon bond axis. So we're going to look at our molecule C2H6 again. Now, as I look from the left here, I get a particular perspective where the front carbon looks like a Y. Notice the Y shape. Alternately, if I look from the right side here, down the carbon-carbon bond axis, notice that the shape of the carbons forms an upside-down Y. Right, this is going to be useful when we start attaching different groups and converting these to and from bond line structures. Right now, we're just trying to understand what a Newman projection is. So the front carbon in our Newman projection, this is your Newman, the front carbon should eclipse the single bond. Notice we don't see the single bond behind that front carbon because it's eclipsing it. And the front carbon is shown as a point, and the back carbon is a large circle behind it. So what we need to be able to do first is convert a bond line structure to a Newman. Then we're going to learn how to convert a Newman back to a bond line. And once we're proficient in drawing Newman projections, then we can learn about the conformational stability of different rotational states by looking at a Newman projection. So that's where we're going. Okay, so the first skill is we need to be able to convert a bond line structure to a Newman projection. And you're always going to be doing this from a specific indicated perspective or angle. So step one, all right, given this angle, right, you're always going to be given or told, or there will be some indication of what carbon-carbon bond axis to look down. So in this case, we're looking down this particular carbon-carbon bond axis. Now, the first step is we want to draw in the hydrogens and simplify the molecule to a basic zigzag template. Now, this isn't necessarily in the book, but I find this extremely useful. It will simplify every single problem to have an identical process. So we want to make our zigzag template, and then we want to look for that Y shape or the upside down Y shape. That's going to help us to get our Newman started. And I highly recommend that if you're having trouble seeing this, use the model kits that are available in the bookstore to build these models, and then you can rotate them around and actually see for yourself. Okay, so what we want to do is create this zigzag template. Now, this first carbon, we'll call it carbon 1 and 2. The first carbon is going to be our front carbon, and the back carbon number 2, or the carbon number 2, will be the back of the Newman projection. So that zigzag template that I'm talking about is we want to create a template and then fill in all the groups. So here's your zigzag template. There's the zigzag, and we're going to fill in all of the substituents into those R positions. All right, so this was the CH3 group. All right, let's focus on the things that are in the plane, right? Just the blue lines that I've drawn. In the plane of the paper, we have our CH3 group, and we have the OH group. Now, it's really useful to put those hydrogens in. So if I have a chlorine coming out of the plane, we can put the hydrogen going back. Now, I could have also, it doesn't matter which way you draw them, I could have put the dash like that and the chlorine wedge like that. It doesn't matter if it's the right or the left because they're represented. What they're representing is the chlorine coming out of the plane and the hydrogen going back. We can't draw them right on top of each other, so they have to be slightly skewed. So it doesn't matter which way you draw them. So we fill in our hydrogens into that zigzag template. Now, when the molecules get more complex, you're going to see the utility of this zigzag template. Our original molecule is already in that zigzag template, but I've done that by design so we can easily put our groups in. So step one, we're drawing in our hydrogens based on the positioning of the other groups. The bromine is already going back, so that means the hydrogen must be coming out. Step one, fill in your hydrogen, and just take notice from this perspective, I'm looking at this front carbon, which has a Y-shaped. Step two, we're going to decide how each group should be placed in the Y-shaped Newman. So our basic template now for any Newman projection, noticing that there's a Y in the front, there's your Y, and we're just going to fill everything in as we go here. Notice if I'm looking from the left here, the dash bonds, so this is a dash, the hydrogen's a dash, will be on your left when you flip this. Imagine rotating this around now. You're looking at this, pretend like you are this person looking at the Newman projection, and see how the left hand is on the hydrogen and the right hand is on the chlorine. Now, if we want to draw the Newman, we see this was on our left, this was on our right, and we have our Y shape. And what's going down? That's the CH3 group. So all we're trying to do is to fit our groups into the correct position. So we have our hydrogen on the left, our chlorine on the right, and our CH3. Okay, so if we're looking from the left, this is a great trick. If you're looking from the left, the dash bonds will be in the left. Front carbon's good to go. Now let's apply this to the back carbon. We're looking from the left, so the dash should be on the left. Now notice how that's kind of down and to the left. There's your bromine. And what's on the right? Your wedge is on the right, so that's your hydrogen. And finally, what's up top in the plane of the zigzag is your OH. So what we've done is we've converted our bond line structure to a Newman projection. Now, like I said in the slide here, just for fun, this was not part of the problem. Let's imagine if we look at it from the other side, if we apply all the same rules, but looking at it from the other side, looking at the same bond axis, just from a different perspective. So step one was to draw in your hydrogens. So we're going to draw our hydrogen there. We have a hydrogen here. So that's what I have here. I've put my hydrogens in. Now that methyl group, that's a CH3. You don't have to do this. It just makes it a little bit easier. Now imagine you're looking from this perspective. What's on your right are these groups down sort of at the bottom of the upside down Y. So from this perspective, notice we've got an upside down Y shape in the front. So that's our basic template that we're filling in. Down on the bottom right, we have our bromine. On the bottom left in the front, we have our hydrogen. And sticking up in the front is the hydroxyl group. So again, if you're looking from the left, dash bonds will be on the left. If you're looking from the right, the dash bonds will be on the right. Now we're looking from the right. Let's apply this to the back carbon. Looking from the right side, our dash will be on the right. So the top back is the hydrogen. The top front, or top left in the back, is your chlorine. And what's on the bottom? Your methyl group. So our two different Newman projections represent the same molecule, just looking at it from different perspectives. It's the same carbon-carbon bond axis, but looking at it from two sides. And this is a really useful trick in the beginning to help you get started putting the groups in the right place. Now, all Newman projections are not going to be as simple as those the first one that we saw. So you're often going to encounter more complex structures. And in these circumstances, it's really useful if you substitute the larger groups with abbreviations. For example, if you see a methyl group, you can just write it ME. If you see an ethyl group, instead of drawing out all of those, you can write it in ET. If you see a long propyl group, you can write it as PR. And if you see an isopropyl group, remember the isopropyl, you can call it IPR. It doesn't matter what you call these, but as long as you know what your designation is. All right, so let's look at a more complex bond line structure and convert it to a Newman projection. Now again, you're going to be given the perspective to look down. So we're looking down to see the carbon-carbon bond axis that I've highlighted here. And step one, again, is to draw in your hydrogens and create that zigzag template. Now, here's your template. We know that that's the carbon-carbon bond axis. So create a zigzag out of it. And you know that your template's going to have something coming out, something going back, something coming out, something going back. So we want to fill the groups into this basic template. Put our hydrogens in. And now from this perspective, remember, if you're looking from the right, the dashes will be on your left side. Oh, sorry, if you're looking from the left, the dashes will be on your left. That's your left side. All right, and if you're looking from the right, the dashes will be on your right. So let's do those first. Now notice we have the Y-shaped Newman from this perspective. So if we want to start over, our Y-shaped Newman from the front and the back, it's just the opposite. It's the upside down Y. All right, if you are looking from the left, the dashes will be on your left. That means the wedge here, our NH2, is on the right. And what's down below? Well, this isopropyl group, it's a lot easier to write IPR than it is to draw all that out. All right, our front carbon is done. Now for the back carbon. Again, if you're looking from the left, the dashes will be on the left. So that's going to be in the lower left. and that ethyl group will be on the right in the back. And what's sticking straight up is that methyl group. Now you can convert this back into a bond line structure, but that's not really necessary. Okay, next, we want to convert a Newman to a bond line. So we just learned how to convert a bond line to a Newman. We're doing just the opposite here. So you have to choose a perspective. There's going to be two correct answers here, unlike the last set of examples where you were given a very specific perspective and you had to draw a very specific Newman projection. Okay, and you had to draw exactly what it looked like from that perspective. Now there's going to be two answers depending on which side you decide to draw the Newman from. If you prefer to look at the Newman from a Y shape, okay, or if you look from the other side, it's the upside down Y. We're going to do both though. I want you to ignore this side for a second. All right, we're going to look at our Newman projection from the left-hand side. So if we're looking at it from the left-hand side, let's focus on our front carbon here. Our front carbon, I've color-coded these. Imagine you're standing on this left side, reaching out with your right hand, grabbing this carbon. Okay, and if your left hand will be grabbing the blue carbons. Now, if you're looking right in front of you, your right hand on the red carbon and your left hand on the blue carbon, just to get that perspective. Now, look at the front carbon. We have a Y shape. Up top are your hydrogens. Let's draw those in to our zigzag template. Right? We're going back to this. The zigzag template is simply an intermediate before we get to the bond line structure. And on the bottom of that zigzag, in the front carbon, is your methyl group. Now on the left, up top, you've got your CH3. And imagine grabbing with your left hand that blue carbon, right? Well, what's right by your hand? The OH group. That's coming out. What's going back behind the plane is that hydrogen. So you can think of almost dissecting this. And from this perspective, everything over here is going to be a wedge. And everything here is going to be a dash. And things that are in the plane of the paper there, the things that are up and down part of your zigzag. All right, let's look at this from the other perspective now, from the other side. Let me get rid of all of this, clean this up. All right. So now we're going to look at it from the right side. And we want to put everything into our zigzag template. So our zigzag template should look like this. Because if you're looking at it from this perspective, notice that's down, that's going to be that. What's up is that. Okay, so imagine dissecting the plane. What's closest to you, what's going to be the wedge are your hydrogens. Your hydrogens. And what's going to be your dashes? We have the OH. There's another hydrogen here. And we've got our methyl and our methyl. All right, so now we've taken both of our perspectives and put them into the zigzag template. The rest is just converting that zigzag template back into a bond line. And remember, bond lines omit the carbons and the hydrogen atoms. We don't write the C's and the H's. Each methyl group is an endpoint, and the corners are your CH2s. So we convert our zigzag template back into a bond line, and that would be one correct answer. And on the left, over here, if you convert this back to a bond line, you get that. These are not different structures. Imagine flipping this over like a pancake. You get the same exact molecule. So there are two correct answers which represent the same molecule, but it's just depending on the perspective that you're looking at your Newman from. So you decide what you're more comfortable with, looking at it from the left or looking at it from the right. It's really up to you. All right, what I'd like you to do is pause the video, give these two problems a try. You're going to convert the bond line to the Newmans, and when you come back, I'll give you the answer. All right, hopefully you were able to give these a shot. Okay, so step one, converting a bond line to Newman, is to draw those hydrogens in. Now, we have our zigzag template, but let's go ahead and put those hydrogens in. And those methyl groups, we can write as CH3 or Me, it doesn't matter. We're looking down this particular carbon-carbon bond axis. We have to decide, are we looking at it, is our front carbon going to be a Y or an upside down Y? Well, it looks like our front carbon is Y-shaped, so that's going to be the front of your Newman projection. And your back carbon was the upside down Y shape. All right, now let's apply our trick. If you're looking from the left, your wedges, or sorry, your dashes will be on the left. So on our front carbon, here's your front carbon right here, that hydrogen will be on your left. And that means that the bromine is on the right, and what's sticking down is your CH3. Front carbon's good to go. Let's look at the back. The back is that upside down Y. We're going to apply the trick where if we're looking from the left, the dashes will be on the left. And if the hydrogen was on the left in the back, then that bromine must be on the right. And what's sticking up is that CH3. So we just converted our first Newman, or first bond line to a Newman. Now on the second one, it's a little bit more complex. Now we have to decide, all right, based on this perspective, we have to come up with a zigzag template. So for that perspective, your zigzag is going to look like this. There's your carbon 1, there's your carbon 2. Carbon 1, carbon 2. All right, so we're going to make everything look the same. Now, this is an ethyl group, Et. This is an ethyl group, Et. And let's fill in our hydrogens. On carbon 1, I've got a methyl, CH3, so that's our dash. And I must have hydrogen coming out. That's our front carbon. On the back carbon, carbon 2, there's nothing represented, so there must be 2 hydrogens there. And remember, this is the perspective we're going to draw our Newman from. So we've created that zigzag template. It turns every problem into the same problem. And now from this perspective, it looks like our front carbon is going to be Y-shaped again. So let's draw that Y-shaped Newman in the front. The back carbon will be that upside down Y shape. And let's apply the trick. If we're looking from the right side, then everything that's a dash is going to be on the right. So see that methyl, it's a dash. We're putting that in the front, on the right. That means the hydrogen must be on the left, and our ethyl is on the bottom. Moving to the back carbon. If we're looking from the right, the dash will be on the right, so the hydrogen will be on the bottom right. Well, they were both hydrogen, so I guess that one didn't matter. And then what's sticking up is another ethyl group. So we've just converted this bond line to a Newman. In this problem, we're going to convert the Newman projections to the bond line. So I'd like you to pause the video, give this one a try, and when you come back, I'll give you the answer. All right, hopefully you were able to give this one a shot. First step in converting a Newman projection to a bond line is to remember there are 2 correct answers depending whether you look from this perspective or whether you look from this perspective. I'm going to use the perspective looking at the Newman projection from this right side. Now, it's also important to note that you cannot use that trick when I said if you're looking from the left, dashes are on the left, and you're looking from the right, dashes on the right. You cannot use that trick when you're converting a Newman to a bond line. That only works converting from a bond line to a Newman. So do not use the trick here. All right, so if we're looking at from the left, it may be a little bit easier if we convert our Newman to something that looks a little bit simpler. So I'm going to just make that a methyl, ethyl, that's a propyl, our hydrogen, our bromine, and our hydrogen. All right, so if we're going to look at it from the left, let's make our template, zigzag template in this case. That's my propyl, that's my ethyl, there's my methyl, my hydrogen, and my bromine. Okay, so if we put our zigzag template in, there's the methyl, there's the bromine, and the ethyl is 1, 2, right? 1, 2. My propyl, 1, 2, 3. And the bond line is complete. Make sure you don't write in the Me or CH3. Remember, the ET. Bond line structures omit carbon and hydrogens. All you're seeing is the bonds between carbon and elements other than carbon and hydrogen. For the next one, we're going to do the same thing. We're going to look at it from this perspective. Let's convert this to something a little bit simpler. There's a zigzag template in this case. going up now. There's the methyl on the top. There's the ethyl on the bottom. You have your hydrogen coming out front. Methyl going back. There's the ethyl. And your methyl. Okay, so we have to convert this to bond line. Let's put our zigzag template in. And my methyl stays. There's that methyl. I have my methyl going back. There's that ethyl and the ethyl. And this problem is now complete.